Okay. So we are now going to introduce relation between Clifford algebras and the Lorentz group, which is quite strange when you think about it. They're two very different things. And using that, we are going to construct some of the representations of the Lorentz group that we derived abstractly the existence in previous lecture. So then the idea is the following. Let's look at let's fix the notation. So let O 1, 3 is equal to the algebra of Lorentz group. Okay. So this is a notation that we have used. So this is a real Lie algebra, 6-dimensional. Right? So dimensional O 1, 3 over R is equal to 6. And in fact, we know how to describe this Lie algebra as a Lie subalgebra of GL4, right? In fact, O1B is the set of Rx belonging to 4x4. Sorry, just not invertible, just 4x4 matrices. Sometimes you just write G for R, which is really an 4R, right? Because we are not talking about group, we are talking about the algebra. Such that X eta plus, so the equation is X transpose eta, sorry, plus, plus eta X equal to 0. Right? But eta was this diagonal matrix 1 minus 1 minus 1. So eta was 1 minus 1 minus 1. Oh, I don't even know. From here, you can easily show that dimension is actually 6. And so imagine if eta was just identity, this would be skew-symmetric matrices. Because in that case, we would be dealing with Lie algebra of the orthogonal group in the case of positive definite metric, which would be that. And so that's, but this is more complicated. So the first task is to show 6 explicit elements in the basis, that form a basis for this Lie algebra. We have already talked about it, but now we have to again write them down and then work with them. So basically what happens is that we have 3 infinitesimal rotations. Plus 3 infinitesimal, plus 3 boosts, basically. 3, maybe I call it infinitesimal boosts. Infinitesimal boosts. So the infinitesimal rotations are obtained by taking derivative of the rotations in 2 of the coordinate planes, x1, x2, x3, 2 of those, and then taking derivative at the identity. And the boosts are hyperbolic rotations along x0, x1, x0, x2, x0, x3. And we did the calculation. So now the tricky thing now is the way you're going to introduce this basis now. So we are not going to write something like x1, x2, x3 and maybe y1, y2, y3 for 3 boosts and 3 decimal rotations. It's a different notation that's going to be introduced. And that's very tricky. That's very, very important. So the notation is this. We just denote these things by m rho sigma, denoted by m rho sigma. So these are matrices belonging to O13. But in the indices rho sigma, this is antisymmetric in rho sigma. Which is they go from 0 to so we have 4 indices, and we have an antisymmetric object, so it's going to be 4 choose 2, which is 6, right? So the total number of these matrices are going to be 6. So the only thing that we have to introduce are the following: M01, M02, M03, and then M12, M13, and M. The rest are going to be obtained from these by using antisymmetric group. Okay, so that's the notation so far. Okay, so these are the 3 infinitesimal boosts. And these are going to be 3 infinitesimal rotations. So, for example, M01, for example, is something that we saw before. So there is 0, 1, 1, 0, and then zero. So this is infinitesimal boost in x0 and x1 directions. One time direction, one space direction. So let me quickly call the boost in x0, x1 direction, and you do nothing on other coordinate systems. And this is, of course, the derivative of these cosine hyperbolic function rotations, hyperbolic rotations in the hyperbolic space at identity. And of course, similarly, you know how to do M02 and M02. You just move these indices. And M12 is also similar. So M12 is, again, so we are like 0, 0, 0, 0, and here is -1, 0, and here is 1, 0, 0, and then there is 0. So there is this infinitesimal rotation. So this is rotation, really rotation in x1, x2 plane. So these are really like infinitesimal rotations in plane of x1, x2. And then we just use for other coordinates. Okay, so that's one thing that is used. Now, these matrices satisfy some strange looking commutation relations. We know the commutation relations for these guys. These are like SU2 essentially, if you complexify especially. But before complexification, this is like an SO3 generators relations. And this one is, there's a similar thing for. But when you take them together, this way of notation, they satisfy the following relation. So let me write it here. Any question? Okay. So we just now write something like this. This is pure computation, but it's an important fact. So I can say maybe lemma. We have the following relation with the bracket of m rho sigma m tau mu. You can tell what the bracket of any two of these things, 6 basis elements, is. So that's eta sigma tau m rho mu minus eta sigma tau m sigma mu, the 4 terms, plus eta rho mu m sigma tau minus eta sigma mu m rho tau. I may have made a mistake here. It might be new. Sure. What this is. Not sure.
There should be a row in the second term.
Which one?
A row is missing.
Oh, a row is missing. Indeed, the first one is row.
And then the second, the top right term.
Oh, this one?
Top right.
Oh, this one.
Sigma tau, sigma mu.
Yeah, this is sigma nu. Yeah, I have sigma tau. Should be sigma rho, you think?
I think the row tau, I think.
Oh,
Because that's the only
yeah, we need
pair
metaphoric
that doesn't appear yet.
maybe, yeah. But this is something that you have to check. When your well-being depends on correctness of this statement, you will check it. But for now, our life doesn't depend on that. So okay, so this is pure computation, but it's very important. That's kind of basis of all these things we are going to do. Okay, now, so that's all we need from the. So that's a real basis for the Lorentz Lie algebra, and that's what we're going to use now. All right, now let's look at Clifford algebra. So this is really like real Clifford algebra of quadratic form. Well, this quadratic form has signature plus, minus, minus, minus. That's quadratic form that's a Lorentz, Lorentzian metric that we are working with, right? Okay, so we can denote it by CL13, right? CL13. So this is the real algebra by definition. By definition, this is the R algebra generated by four generators, gamma 0, gamma 1, gamma 2, gamma 3, subject to relations. Subject to the following relation, the anticommutator of gamma mu and gamma mu, anticommutator of gamma mu is equal to gamma mu plus gamma mu gamma mu. Which is, I mean, by definition, equal to that. This is equal to 2 eta mu identity. Okay. I mean, in particular, of course, gamma 0 squared is equal to identity if you go to the relation, and gamma I squared is equal to minus 1, or I equal to 1. So this is an abstract algebra, the way it's defined, and the relation between these relations and these relations is not clear. I mean, this is an associative algebra. It's not a Lie algebra, but this is a Lie algebra, and the nature of relations is different. But still, we will find some connections now soon. Okay. Okay, so this is a real Lie algebra with the unit is not commutative, but as we discussed briefly last time, we can show that this is actually so this guy has a nice irreducible representation. So I mean, so let me write some facts about it. First of all, dimension of this guy over R is 16. You know that. I mean, it needs a proof, but that's okay. Dimension of CL 1, 3 over R is 16. And this has a unique irreducible representation. I'm claiming even a unique real irreducible representation. So let me start with this irreducible representation of CL13. In other words, what I'm saying is that there is an algebra map, maybe I call it chi, I mean, it's just from CL13. So this goes into the algebra of 4x4 matrices, but with complex coefficients. Okay, so into M4 C. But this is only a real algebra. Okay, so and what I'm saying is that this is a real algebra map. So here we forget about complex structure. So this is a real algebra homomorphism. I mean, which is in fact injective. So how does it work? Well, we have to construct 4 matrices. inside 4x4 matrices that satisfy those relations. And so those 4 matrices, there are basically 3 choices, 3 canonical or preferred choices that this is used. So let me just write it. Okay, so let pi of gamma 0 be equal to the following 4x4 matrix: 0, 0, identity, identity. Okay, and then pi of gamma I equal to 0, sigma I minus sigma I, 0, for I equal to 1, 2, 3. So these sigma i's are Pauli spin matrices. Pauli spin matrices. And these Pauli spin matrices, we know that they satisfy the relation sigma I, sigma j. The anti-commutator of sigma I, sigma j is equal to 2 delta ij. Right? Then they satisfy this relation. And using this, you can show that these guys satisfy the relations of Clifford algebra relations. Okay, so check. This is something that we can check indeed. So this is a star. Star implies that pi of gamma I equal to 0, 1, 2, 3, satisfy Clifford algebra. So that's what we see in these relations. Another thing that we know is that this is the smallest possible representation in terms of dimensional matrices. And we know that this is irreducible. Another thing is that there is another fact that maybe I'll just write it. The fact is that any other representation is going to be conjugated by conjugate of this. Any other rep of CL13 in M4C is conjugate. Above, i.e., there exists V belonging some invertible 4x4 matrix. Such that basically, any pi nu is equal to E pi V. Because this pi is so any other representation. So pi nu, you can always write it for conjugation. Obviously, if you take this set of matrices and conjugate it by an invertible, you're going to get a set of matrices that satisfy the relation. So you have a lot of freedom in choosing. If you know that there is one representation, then you know that there are infinitely many representations. And That's but this is good to know. And so basically, what happens is that there are three sets of representations that are preferred in physics. One is while, so we have to learn these things now. Actually, I'm not sure exactly which one is this, but this is one of those three. So I believe this is while or chiral representation. So we have while representation. We have Dirac representation. And we have Majorana representation. So these three sets of representation. This is while. This is also called chiral or chiral representation. Yeah, I'll get to that soon, but this is why. The Dirac, I will write Dirac soon too. Okay. So anyhow, so we have this Clifford algebra, we have these matrices. Now we might ask, okay, so what? So what? What are you going to do with this now? Yeah, now here comes the main thing. So this thing, you see, yeah, let me write it down and then we compare with the construction that we did before. So maybe this comes under the general heading of relation between Clifford algebra and the Lorentz group. I mean, Lorentz Lie algebra. Okay, so now you introduce now using these Clifford generators, we introduce some new elements inside this Clifford algebra. So consider the elements. So S rho sigma equal to quarter of gamma rho gamma sigma. Quarter of gamma rho gamma sigma. Okay. So now this is equal to check, of course, 0 if rho is equal to sigma. You see, this is the commutator. The other one was anti-commutator. So if rho and sigma are the same, they cancel. So this is 0, that's obvious. And you can just check that this is equal to half of gamma rho gamma sigma. Yeah, I mean, that's also obvious because you use anti-commutation, you change minus this to the 1, and then you get two factors with quarter, they give you half of the quarter of 2 is half. So that's pretty obvious from the relation. Now, so here is the main claim that actually these matrices or these elements satisfy exactly the same relation as the generators of the Lorentz group M sigma rho. That's quite something. So the claim is that S mu mu. Okay, so I mean the claim really is this. The yeah, S mu mu and S rho sigma, any two elements like that. The commutator is equal to eta mu rho S mu sigma minus eta. Again, I'm writing. So this is mu rho. This is mu rho. S mu sigma was eta mu sigma S mu rho minus eta mu sigma S mu rho. Okay. So that's this one. So the relations that I wrote for m rho sigmas are exactly like this. Maybe there isn't there's some change of, maybe I made a mistake in the first term, but that's okay. So this is exactly same as relations between m rho sigmas. Okay. So now what can we do now? Well, now we have got a representation of Lorentz group. Right? We've got a representation of Lorentz. So let's call this a star now. And everything that will be using a star plus representation pi of CL13. Now we are going to get a representation of Lorentz Lie algebra. O13 to the 4x4 matrices, GL4, right? Little GL4. And 4. Or basically, the basis that we have here, M rho sigma, gets mapped to S rho sigma. That's it. S. So this is now a real representation, because this is a real map. It's a real representation of the Lorentz Lie algebra. Oh, I made a mistake here. Sorry, this is 4. I mean C. Actually, I'm not sure you can represent it inside real 4x4 matrices. I'm sure. It's a bit subtle. Yeah. Yeah. Now, one thing that we have to notice is that this representation is not the what's it called? The standard representation of the Lorentz group. That's a different representation, and that's important. So important. Of course, we have an obvious representation of 013, right? This is called the standard, of course. Width of 013. I mean, what is it? Because we know that this Lie algebra 013 is, after all, you know, is a sub-Lie algebra of GL 4R, right? And this is inside GL 4C, right? I mean, this is a Lie algebra of that, and hence the algebra of that. So you have an obvious, I mean, because these Lorentz matrices, I mean, n sigma mu's are 4x4 real matrices, actually, in this case. So they can be considered 4x4 complex matrices. And that's it. So it's already kind of God-given representation. And there is this one now. There is this one. The claim is that this and that are not the same. These two representations are not the same representations. And that's very important.
Also not conjugate.
Sorry? No, they're not conjugate. Now we are talking about representations of Lie algebras, not Clifford algebra. You see, the conjugate business was for Clifford algebras. The Lie algebra and groups are different.
Yeah.
So this is the first subtlety we have to bear in mind. And actually, it would be good to understand why they are not equivalent. Something happens, which is quite deep. By the way, this representation, the standard representation, is also called vector representation. This is a famous, this is called vector representation. Okay. So that's what we have. Okay, now we can define what we mean by Dirac spinor, where the Dirac things operate or acting on. It's in this representation, not in the standard representation. So let me make a definition. So definition. A Dirac spinor. Yeah, is a map. You can call it a field. Psi from R4 to C4. So we just write x to psi alpha of x. Now, this alpha is a different indexing now. We are using index in the fiber now. This 0, 1, 2, 3, we're indexing the space-time index. But this is index in the fiber, which goes from 1, 2, 3, 4. Alpha equal to 1, 2, 3, 4. That satisfies the relation that is acted on that's acted on Lorentz group by this by our this new here this rho sigma representation, i.e. for any lambda belonging to the Lorentz group. Now I'm going to use the notation for the Lorentz group, not think. So yeah, that's a bit subtle, but okay. So let's just start to my notation was capital O, which is Lorentz group. Fine. So this I wrote it once before, so I found this is equal to S of lambda psi lambda inverse of x. Now there is a warning I have to make here. The representation S that I introduced was only on the level of Lie algebras, right? Our S was first on the Lie algebra. So, so what was it? I mean, we just had representation. I called it S from little O13 to and it is a fact that this does not lift to does not come from representation of the Lie group. It's not infinitesimal representation of a representation of the Lie. So this so fact is that this cannot be lifted. I mean, there is a spin here. This cannot be lifted. To, like the relation between this spin group and SO3, spin 3 and SO3. But the representation, the trivial representation that I had, the vector representation comes from representation of, because the Lorentz group is also inside GL4. So while the vector rep is made from a graph of so it's rather problematic to write even this relation, because I'm assuming that this S now is acting on this thing which is not quite correct in a way. So there is an ambiguity in this thing, in this statement. Okay. When it comes to more serious stuff, we will address this question. But right now, there is this issue that question.
Yeah. So you said if we were going through this, if it can't be listed to the Lorentz group, why can we even fight that?
I mean, because physicists write it. And well, they say a spinor is a quantity that if you move around, when you come back to the origin, like you go around the z-axis, come back to the origin, it's gone. So it's not in this sense, it's not a continuous object, but still they can work with it. So. I mean, I know that my answer is not perfect. It needs more elaboration, but there is this subtlety because the Lorentz group is not simply connected. It's pi1 is z2. We calculated that, right? It's definitely not connected. It has 4 connected components, but it's also not simply connected. There is exactly like exactly like O3, which has 2 connected components, but the connected component is not simply connected. It's exactly coming from non-simple connectedness of SO3, actually. That's a kind of piece that's there.
That's a question.
Yes.
Do we know anything about irreducibility of the?
Sorry?
Are they irreducible or reducible?
This one?
Yeah.
I believe this is not irreducible. I think it can be decomposed as Dirac sums of 2 sub-representations. Each of them are 2-dimensional, complex. So as a complex representation, it's so again, I have to be very careful. I don't think so. The short answer is I don't think it is irreducible. It decomposes, and I will write down a version of this which will show that it's decomposed. But there is a subtle, again, another subtlety is there is this issue of complex representation versus real representation. That all brings another layer of complication. So that's what it is. Yeah, I mean, for example, okay, so what else we want? Okay. We are basically through now, but there is one thing that's maybe before we leave, you maybe see if I have power. Oh, I have good. I just mentioned, and that's the constructing now relativistic invariant equations. Okay, I mean, maybe I just erase this. So relativistically. Invariant equations. So you remember the general setting was like this. So we said let V be a representation of the Lorentz group. Now we are talking a little bit general and ambiguous, but that's okay. Let I from O 1 3 to GL B be a record Lorentz group. So once you fix the representation of Lorentz group, then you can consider the following situation. So you have this R4 cross V, right? So this is like R4, and your fibers are V. So this is like a trivial fiber bundle, or trivial vector bundle. Right? We will look at this trivial vector bundle. And our fields now are sections of this trivial vector bundle. So fields is sections of this. Okay, so I mean, because everything is trivial here, so basically fields are size from R4 to V. I mean, we had one example like Dirac fields that goes from R4 to C4, and notwithstanding the question of lifting of that representation to the Lorentz group, imagine it is, then this is a field with respect to that representation. But this is very general. So imagine you have some equation that's acting on some differential equation that's acting on these fields, like P of psi equal to 0. I mean, in the case of Dirac equation, I gamma mu d mu minus m psi is equal to 0. This is the famous Dirac equation. So as if you just look at it as an equation, so what is it? I mean, it's nothing special, but we want to check that this is relativistically invariant. So what does it mean to say that P is relativistically invariant? I defined it before, but we say P is relativistically invariant if we say is relativistically invariant if I mean the following is happens if psi is a solution, if psi a solution implies that the action of on psi by any implies that psi prime, psi L is also a solution where psi L of X is this new field, which is so we have got the representation pi psi of, pi of lambda, sorry, psi of lambda inverse of X. We are just basically conjugating our field. So what does this mean? It means that if you introduce a new coordinate in R4 and a new coordinate in V, if you write the equation of the field in this new coordinate, and that's exactly this. This action is nothing but writing the equation of this field in this new coordinate in fiber-wise and phase. It should be a solution again. Well, what new coordinates you can choose? You can choose only new coordinates that are relativistically equivalent to each other. So, for example, if someone is moving with some speed v and using boosts to translate from one system to another system, they shouldn't disagree on whether I have a solution of my equation or not, because coordinates is just an artificial thing. It's not the real thing. Coordinate is just a device. There's no God-given coordinates in the universe. All these coordinates that are obtained from each other using the Lorentz group are equivalent. But the deal thing is that we're also acting on the fiber. That's important. Because there is also no natural coordinates in the fiber. You can introduce different coordinates. I mean, in this sense that you change from one. Yeah. Okay. Now, if we agree that this is a good definition, this is what. Now, checking that, for example, Dirac is relativistic invariant, this equation is relativistic invariant. It's kind of some work, actually. It's not straightforward. It's a pain. So, what's the solution to this? The solution is that we are going to derive this equation from a Lagrangian, and we just check that that Lagrangian is relativistic invariant. That's easier. Once you check that your Lagrangian is relativistic invariant, then you're guaranteed that the solutions are, because it's like this. You have a function that's invariant under the action of a group. Then, of course, that group sends critical point of the function to itself. For example, imagine you have a function that's invariant under a group, and you look at the minimum of this function. The minimum, again, is sent to a minimum. You cannot send to something bigger because it's invariant. Also, critical points in general, you can write down the equation. So that's a very nice logic. So what we are going to do now, we are going to show some ways of constructing quantities that are some scalars that are relativistic invariant, and then that would lead to this, for example, a single function. So that's the strategy that we take. Any questions? Or? Yeah. There is another Dirac equation, which is the plus. There's also Weil equation, which is like for 2 by 2 spinors. And there is, well, yeah, I mean, the first one is actually the simplest one, which is the Klein-Gordon equation. So let me write it here. But in the case of Klein-Gordon, things are much easier. So here is an example. The G equation. So what is KG equation? Well, what is V? In this case, V is equal to, actually, you can say R or C. And trivial representation. And pi is trivial. So it's doing nothing. So what are fields? Fields are just Klein-Gordon fields going to R or C. So these are KG fields, right? So what is Klein-Gordon equation? It's box plus M2 psi is equal to 0. Is there a?
No, I just thought that was thinking.
Something, you know, box, we have got box, yeah, plus M2 psi is equal to 0. So now what is box? Box is just the box operator, which is the wave operator. Okay. And checking that this is relativistic invariant actually is easy, because in this case, the way that these things, fields, the way that Lorentz group acts on fields is only on the base. It's not on the fiber, because fiber is trivial. Psi L or psi lambda of x is equal to psi of lambda inverse of x. And all of this boils down to the fact that the Laplacian of a Riemannian manifold or Lorentzian manifold is invariant under the action of the isometry group, which is very reasonable to believe, and you can check. But this is first order, and that's much harder. Okay, so I think for now we are good. So, so this was the thing. So I will